This summer, we sought to investigate airship propulsion from perspectives of design, automation, and experimentation. Lighter-than-air vehicles offer unique advantages over traditional aircraft. Unlike airplanes and helicopters, an airship doesn't consume fuel for lift, can hover indefinitely, and can travel long distances without requiring an airport or ground control. However, developments in airship technology have severely slowed since the Hindenburg disaster of 1937. We can redesign the Hindenburg for the 21st century and inspire renewed interest in lighter-than-air vehicles. This is the Zephyrus. We designed an airship to fulfill the requirements of safety, efficiency, accessibility, responsible aviation, and transportation. Unlike traditional airships like the Hindenburg, Zephyrus uses a rear fin to propel itself forward, much like a dolphin. Here, we see that the dolphin leaves behind a much calmer wake than the speedboat, despite traveling at comparable speeds. Clearly, dolphin-style flapping is much more efficient than traditional propellers for thrust. The design for Zephyrus includes a rigid airframe with the shape optimized computationally to minimize drag. The dimensions of the Zephyrus are based on measurements of an actual dolphin. Below we see a cross-section of the hull of the Zephyrus. Each of the 14 gas cells is filled with hydrogen. Most airships today are filled with helium, but due to the current helium crisis, we believe renewable hydrogen is a more environmentally responsible lifting gas. The hydrogen will be regulated through a system of high-pressure tanks and air compressors that allow the pilot to manually adjust the volume of hydrogen in the hull to control altitude. We've taken several safety measures to prevent the flammable hydrogen from igniting and causing another Hindenburg disaster. Double-walled gas cells will prevent leaks and slow the rate of burning in the event of ignition. If total hull combustion is inevitable, gondolas suspended from the hull will function as gliders to carry passengers and crew to safety. We've 3D printed a scaled model of the Zephyrus. Here you can see the dorsal fin, which provides stability for roll, as well as the pectoral fins, which control yaw. We think this basic design can serve as a basis for a more complex design in the future.
In order for flapping fin dirigibles to become a viable option in the future, flapping motion must be autonomously controlled. The scope of this project was to investigate autonomous control for flapping fin propulsion on lighter-than-air vehicles. Our object was twofold: understand what factors influence flapping fin propulsion, and develop simple, open and closed-loop controllers. The platform we used to test autonomous control was the commercially available Air Swimmer's toy. The Air Swimmer is a large helium-filled balloon measuring 57 inches in length and 36 inches in height with fins. A small DC motor mounted at the back powers flapping. Autonomous control is enabled through an Arduino microcontroller board mounted at the rear on the underbelly of the fish. This video shows one of the best runs using open-loop control. An open-loop controller does not use feedback. The objective of our open-loop control was to program the Air Swimmer to fly a pre-programmed path as accurately as possible. We were able to successfully make the Air Swimmer fly 20 meters forward, turn right, and return to within 3 feet of the starting position. Despite the simplicity of the code, it was extremely difficult to achieve straight motion. The main source of error was the DC tail motor. The motors that Air Swimmers use have clear left or right biases, which change with time. As power bias changes, so does the mean angle of flapping, which causes the Air Swimmer to turn. In order to achieve symmetric flapping, we had to observe the natural bias of the motor and offset accordingly. If the motor had a left bias, we decreased the motor power to the left side or increased the motor power to the right side. This is a video of a successful closed-loop run. In contrast to open-loop control, closed-loop control uses feedback and adjusts output accordingly. In the case of the Air Swimmer, the output was the motor signal, and the monitored variable was the distance measured by 2 ultrasonic sensors mounted to the front of the Air Swimmer. The Air Swimmer begins by flapping forward. Then the ultrasonic sensor distances are read. If the Air Swimmer is too close to the right wall, it kicks to the left, and vice versa. The greatest source of error in our closed-loop control was the wobbling caused by flapping. Because of wobbling, the ultrasonic sensors measured the diagonal distance instead of the perpendicular distance to the wall.
Okay, so how do the sensors actually work?
Okay, so these are ultrasonic sensors, and they calculate distance by sending out a sonic ping. So the sonic ping is a sound wave that travels forth and bounces off the closest object or surface. The sensor sends a sonic ping and records the time it takes for the ping to return, and then it uses the speed of sound to convert that time into a distance.
Okay, so for the closed loop part, were 2 sensors enough, or do you think with more sensors it would be better?
we theoretically thought that two sensors would be enough because two sensors allows you to measure from the right and left sides. The problem was that the wobble introduced a third dimension, which was the angle of the fish, and the sensors could not capture that. So if we had another sensor, we could potentially capture the angle of the fish, and that way we could better predict for the diagonal distance that the fish was measuring instead of the perpendicular distance.
So why did you not add a third sensor?
The problem was that this helium-filled balloon has a very limited weight capacity. A fully inflated air swimmer has a weight capacity of about 60 grams. And with the two sensors, the Arduino, the H-bridge, the 3 batteries we were using, we were right at the limit of that 60 grams. So 3 sensors could not be supported because if there were 3 sensors, it would just sink to the bottom.
Okay, so what do you think you can do in future? Like, if you want to add 3 sensors, do you want to add more fishes to it? Something like that?
So the biggest problem with the closed loop control is that the hardware and this testing platform has a lot of problems of its own. So before we can do a good job of testing different control methods, we have to improve this platform. So our biggest suggestion is to improve the lifting capacity of the air swimmer so we can have a better electronics, such as a better microcontroller or processor. This would allow us to get a higher sampling rate, because right now the ultrasonic sensors only read distances once per flap. The other thing is if you take 2 air swimmers side to side, the mirrored flapping of 2 fins has the ability to eliminate wobble. And if you eliminate wobble, it makes sensor readings much more accurate.
In addition to understanding automation and control of dirigibles, we must also investigate propulsion systems through experimental wind tunnel testing. Our next study aims to contribute to dirigible design and optimization by using a novel form of propulsion, bio-inspired fin flapping. Aquatic animals generate thrust by oscillating their flukes and fins, allowing them to propel underwater. The traditional wing is a rigid foil with 2 degrees of freedom, whose main objective is to achieve lift, while the flexible caudal fin in neutrally buoyant aquatic animals enables them to generate thrust. Studies have demonstrated flexibility can potentially increase thrust generation. Under conditions of efficient propulsion, 2-dimensional flapping fins have been shown to generate 2 spanwise vortices per oscillation, which resemble a Kármán vortex street, except with the polarity of the vorticity reversed. Strouhal numbers are used to characterize wake patterns. F is the driving frequency, A is the peak-to-peak amplitude, and U is the flow velocity. 2 parameters of interest are Strouhal number and aspect ratio, which strongly correlate with thrust generation, which we investigate experimentally. Howdy, I'm Alex. I'm with the experimental group. Come and see. We're a group of summer researchers working under Dr. Garamaji. This summer, we aim to study the effects of flexibility on thrust generation. To swim or not to swim? That is the question.
What do you have there, Alex?
Glad you asked. This summer, a group of researchers and I decided to study the aerodynamic effects of a forebody in conjunction with a flapping fin. However, we discovered that there was a more fundamental problem in understanding the efficacy of flapping-based propulsion. In an airplane, the wings are rigid, with the main objective being to generate lift. However, in aquatic animals that are naturally buoyant, they don't need lift. Instead, their main objective is thrust. We sought to study the effects of flexibility on thrust generation. We did this by creating 3 different fins of various flexibility. One that was rigid and stiff, one that was overtly flexible, and one that was somewhere in between, with semi-flexible. Oh, hey there. Just finished working on the MFC, the Multiple Flapping System Experimental Apparatus. So here's the MFC. Most of the components have been rapidly prototyped and manufactured in-house at Texas A&M. Here we have our 0.2 degree resolution stepper motor. The shaft is attached to the crank, which generates a 45 degree amplitude. As you can see in these sleeve bearings, we can actually change the amplitude that is generated to be experimentally tested. The crank is connected to the shaft by the coupler. So here we have the rocker arm attached to the shaft down here, which is also in turn connected to the load cell. The load cell is a 6-component strain gauge that measures X, Y, Z component forces as well as 3 moments. Now we're ready to mount the fin. As you can see here, we have a threaded standoff. This enables us to thread into the 1/4-inch shaft in the wind tunnel easily and effectively. Here we have the electronic setup. We have a 24-volt AC to DC converter, as well as a driver that communicates to the motor. Wired here, we have a USB that connects to our computer in which we put our input frequency. Now we're ready to turn on the wind. We're testing at 3 different flow velocities, 2, 3, and 4 meters per second. Coefficient of thrust was plotted against true whole numbers ranging from 0.05 to 0.35. Peak thrust coefficient was observed around 0.25 for all fins, with a semi-flexible fin generating the highest thrust coefficient at 2 meters per second. While these results are preliminary, they indicate that the MFC has yielded repeatable data, demonstrating its role for future research. We hope that our work this summer will pave the way for future developments in airship technology. Research and design, automation, and experimentation may one day lead to a future for the past.